Fine. So screen is visible now.
Yes, sir.
Okay. So after what we have done in the previous class in organometallic chemistry,
Reactions of metal carbonyl, substitution reaction, associative and dissociative.
associative and dissociative, that nickel carbonyl species example we have done, right? NiCO whole 4.
Oh, yes, sir.
Okay. Fine. So next, suppose you have this. Suppose you have this example, chromium CO whole 6. Okay. This is the example you have, compound you have. Now you are treating this compound with this ligand PME3, okay, trimethyl phosphine. So yeah, can you tell me which mechanism it will follow, associative or dissociative mechanism? Which mechanism it will follow?
Dissociative mechanism.
Dissociative mechanism. So if you see chromium, so how many electrons chromium has? 3d5,
6, sir.
4s1, right? 6, yeah. And from 6 carbonyl you will get 12 electrons. So total you are getting 18 electron from this complex. And if you have total 18 electron, so it cannot undergo associative mechanism. It has to be dissociative mechanism. Okay, dissociative mechanism. Okay, so what will happen? So suppose you have this, I am drawing here. So basically it will be an octahedral complex like this. Okay, so you have carbonyl here. So what will happen? One of the carbonyl first of all will leave from this complex. Okay, so basically you can show minus CO. Okay, and if one of the carbonyl leaves from here, so basically what you will get? What you will get? Here you will get a vacant position. Now this position is becoming vacant, right? So what is the ligand we are using now? PME3. So phosphorus has
PME3.
lone pair, yeah. So basically phosphorus will come to this position, right? So better I can write down like this. Okay, I can write down like this. PME3 is binding now with the metal center like this. Okay. Now next step, suppose I am giving another PME3. Okay, PME3, and temperature is your this 80 degree centigrade temperature. So what will happen? Another carbonyl group. Okay, another carbonyl group will be replaced by this PME3 ligand. Okay, another carbonyl group will be replaced by this PME3 ligand. Okay, so like that. Okay, fine. Now if you incorporate, so another thing is here, that is actually you have to be noted. So initially when you incorporate one PME3 here, the temperature required for this reaction is 25 degree centigrade. So that means normal your room temperature. Okay, the reaction is happening in room temperature, but in the second step you have to increase the temperature 80 degree centigrade. Okay, now suppose I want to add another PME3 ligand in this compound, in this complex. So that time the temperature required is 110 degree centigrade. Okay, 110 degree centigrade. So can you tell me why the temperature is increasing, like why we need higher temperature? Why we need higher temperature? Hmm? Why we need higher temperature? So if you see here, when PME3 comes, so basically phosphorus is binding with this ligand, that is fine. But if you see, phosphorus is donating electrons, right? Phosphorus has a lone pair. Okay, basically it is donating the electrons to the chromium center, right? So it's an electron, I can say this is a sigma donal ligand. Okay, sigma donal ligand. And basically electron density on your metal center is increasing if you use this PME3 ligand. Okay, so if you use this PME3 ligand, the electron density on chromium center will increase, and if the electron density increase, so chromium will back donate the electron density to the carbonyl, okay, to the vacant pi star orbital of carbonyl. Try to understand. PME3 is donating the electrons, lone pair. So electron density on metal center is increasing. Now metal is back donating the electrons to the pi star orbital of your carbonyl group. Okay, and what is happening? This chromium carbonyl bond, okay, this bond becomes strong. Okay, this chromium carbonyl bond is now becoming very strong bond. Okay, this chromium carbonyl bond is becoming strong. So similarly, when you introduce two phosphorus, like two PME3 group, so they are donating electrons to the chromium center, and chromium is also back donating electrons to the pi star orbital of carbonyl. So that means here these two chromium carbonyl bond, these two bonds, this chromium carbonyl and this chromium carbonyl, they together becoming what? Strong. When I am introducing further PME3, so that time suppose here also, here we have 3 PME3, right? 3 PME3, and I can say that all the chromium carbonyl bond are now becoming strong. So here all the 3 chromium carbonyl bond is now becoming very strong. And if your chromium carbonyl bond is becoming strong, so if you introduce one PME3 group, so that means one of the carbonyl has to release, right? Because it has already 18 electron, it cannot follow associative mechanism. Dissociative mechanism it will follow. So first step is cobalt, this CO ligand will leave from here, and if your bond is becoming strong, so that means you need higher temperature, higher energy, right? So if you increase the temperature, the energy will increase and the bond will break. So that is the reason why the temperature is gradually increasing. Okay, clear? Any doubt? Any doubt?
No,
So
sir.
this is the major product. Okay, this is the major product. Further introduction of PME3 group is not possible. Why? Why not possible? Because you can see here you have 3 PME3 group, 3 sigma donal ligand, and you are getting this 3 chromium carbonyl bond is now becoming very strong. So it cannot further dissociate. Okay, so that will be your major product. Okay, this one is your major product. Clear? Any doubt?
Yes, sir. No, clear.
No, right, fine. Okay, now suppose you have this molybdenum CO whole 6. Okay, so now you will see some reactions, basically how to do the reactions. So this is your benzene. Okay, benzene in presence of heat, what will happen? Okay, here you write down this compound 1 2 3 4 5 6 7. So here you have 1 bond, 2 bond, 3 bond. Okay, in presence of heat. Okay, now here you have this. Okay, now this side you have this ligand 1 2 3 4 5 6 7 8. This is your cyclooctadiene. Okay, this ligand is your cyclooctadiene. This is generally represented by COD, cyclooctadiene. Okay, another one is your DPPM. Okay, DPPM in presence of heat. Okay, CO280, and this is your inorganic chemistry you have done, CO280. So now you have to do the reactions like what will be the product if you react this compound molybdenum carbonyl complex with all of these yeah, all of these compounds, what will be the product. So first of all tell me like how many electron system it is, this molybdenum carbonyl.
18 electrons.
18 electron, right? So if it is your 18 electron compound, and here what you have, benzene, right? So benzene contains how many electrons?
6 electrons.
6 electrons. So here you have 6 electron, here you have 18 electrons. So definitely it will follow your dissociative mechanism, not associative. So basically you have to introduce like this. Suppose you have molybdenum, this is the metal center you have. Now this side suppose you have benzene. So benzene has 6 electrons. So benzene, like all the 6 electrons will donate the electrons to the molybdenum center. Okay, all the 6 electrons will donate uh, all the all the carbon atoms, or the whole benzene group will donate all the 6 electrons to the metal center, molybdenum center. So basically molybdenum you have 6 electron, from benzene ring you are getting 6 electrons, so 12. So how many carbonyl left? 3.
3.
Okay, you can see 6 plus 6 plus 6, right? 18 electron you are getting. Fine. Now suppose you have this ligand. Okay, this is basically your cycloheptatriene. So here also you have how many electrons you have? 1 2 3 6 electron you have, right? So
Yes.
again you can show it like this, that 1 2 3 4 5 6 7. So here you have one double bond, one double bond, one double bond. Okay, so suppose this side you have molybdenum, so you can show like this. Okay, all the pi bond is donating the electrons to the molybdenum center. So 6 electrons from here, molybdenum has 6 electrons, and how many carbonyls will left now? Again 3, right? Because
3.
total electron count will be 18, not more than that. Okay, total electron count will be 18, not more than that. Now if you have this
In this CO, 1 CO left.
huh?
1 CO, 1 carbonyl will left.
Why?
No. This one.
This one.
Yes, sir.
Why one carbonyl? How many electrons you have from this cyclobutadiene?
4.
4 electron,
4.
right? So try to draw the structure. So this one. Here you have molybdenum. So this pi bond donates electrons, this pi bond donate electrons. So 4 electrons from here, 6 electrons from your molybdenum center. So how many carbonyl left? 4 6 10.
1 carbon.
8 electrons.
10.
8 electrons, no?
Yes.
So how many carbonyl? CO whole 4.
4.
Okay, not one carbonyl. If you see this one, cyclooctadiene, so first of all draw the ligand. Okay, so cyclooctadiene. So this is donating electrons to the molybdenum center. This pi bond is also donating electrons to the molybdenum center. So what do you have? So 4 electrons I am donating from here, this ligand. Molybdenum has 6 electrons, 4 6 10s. How many electrons left? 8 electrons left. So that means this molybdenum will have 4 carbonyl groups, CO whole 4. Okay.
Yes, sir.
Next you have DPPM. So DPPM means your diphenyl phosphoryl methylene group. Okay, diphenyl phosphoryl methylene group. So it basically shows like this. So this is your CH2. This CH2 is attaching with 2 phosphorus. Diphenyl means you will have 2 phenyl group here. Okay, so diphenyl Okay, phosphoryl methylene group. Okay, so this is the ligand you have. This dppm means this ligand you have. So you can easily see this phosphorus will have a lone pair, this phosphorus has a lone pair, right? So it is donating the electrons to your molybdenum center. This phosphorus is also donating the electrons to the molybdenum center. So how many electrons it is donating? This ligand 4 electron, molybdenum has 6 electrons, so overall you will have 4 carbonyl left. Clear?
Yes, sir.
And this is the last one. So here you see you have only one pi bond, so basically you have 2 electron. Okay, so just draw the ligand CO280 CO280. Here you have double bond. It is donating the electrons to the molybdenum center. Okay, and you can see, so
CO5.
molybdenum has 6 here, right? Here you have 2 8, so that means how many
CO5.
carbonyls left? 5 carbonyls. 10 electrons from carbonyl center, 6 electrons from your molybdenum center, and 2 electrons from this ligand. Clear?
Yes,
Any
sir.
doubt?
Clear.
Any doubt?
No, sir. Clear.
Clear, right? Fine. Okay. So this thing you know, cyclopentadiene, right? This is what? This is your cyclopentadiene. So basically what happens, this actually does not exist like this in monomer. Okay, so write down one line that at room temperature, okay, at room temperature what happens, it exists in dimer. It exists in dimer. Okay, so how the dimer is forming? So suppose you have cyclopentadienyl, so I am drawing it like this. Same thing, see, same thing. 1 2 3 4 5 5 membered ring, you have 2 pi bond here. Okay, and another cyclopentadiene I am drawing like this. Okay, so what will happen now? Pericyclic reaction, Diels-Alder reaction will happen. So this is your 4 pi electrons, and suppose this is your 2 pi electrons. So in presence of room temperature only, okay, what will happen? 4 pi plus 2 pi, 4 plus 2, cyclic addition will happen. So these electrons will attack here, that double bond will attack here, and this pi bond will move to here. This is a simple pericyclic reaction, Diels-Alder reaction. So what I am getting, I will get this compound. See, this double bond is shifting to here. So basically place the double bond here. Here you have this Norboran type of system, and this side you have a 5 membered ring. So 1 2 3, here you have 4 5, and this side you have a double bond. Okay, so this is basically the dimer. Okay, like in room temperature it exists like that. Okay,
Yes, sir.
this is the dimer. But what will happen if you further heat this compound, if you further increase the temperature, so this bond will break. So how it will break? This bond will come to here, this bond will go to there, and this bond will come to here. So ultimately what you are getting? Check. If this bond breaking takes place, so what you are getting? You are getting this thing, na? This one plus what? This is what? This is again you are getting back your cyclopentadiene. Okay, so at room temperature they will exist as dimer. So if you want specifically one cyclopentadiene, so you have to increase the temperature, you have to heat this like you have to increase the temperature from your room temperature. Okay, if you do that, it will exist as your monomer. Okay, Now if you treat this compound with NaOH, so NaOH is a base, it will abstract the proton from here because these are the acidic protons. So NaOH will abstract a proton, and once it abstracts the proton, you are getting this. This is a aromatic system. Okay, clear?
Yes, sir.
So this thing
Yes,
will
sir. Clear.
happen. Yeah,
Sir, in presence of temperature,
in presence of
what will happen?
if you increase the temperature in room temperature, it will exist like this dimer. So room temperature means normally you're 25 degree centigrade, but suppose I am increasing the temperature to 40 degree 50 degree, that time it will exist as your monomer. Okay.
Okay.
uh, okay, one reaction try to do. Suppose you have this 2 moles of this compound molybdenum CO whole 6. Okay, and you have this dimer basically. Okay, you have this dimer. Okay, so this is also your dimer thing. Okay, in presence of H nu, what will happen? So this is the question, try to solve. So you have 2 moles of this molybdenum CO6 compound, you have this dimer of cyclopentadienyl. In presence of H nu, what will happen? Try to solve it, do it. Tell me what will happen. So here if you see, so if I mention this H nu, so that means in presence of light, so you are providing some energy. Okay, so you are providing some energy, and if you provide some energy, so basically this dimer will lead to, like this dimer will now gives you two monomer. Okay, so basically the pericyclic reaction will happen. Okay, and you will get 2 cyclopentadienyl ring back. Okay, this reaction will happen. You will get these 2 cyclopentadienyls back, and so once you are getting these 2 cyclopentadienyl rings back, so you know, right, you know. So what will happen? So molybdenum. Okay, so this side, suppose you have 2 cyclopentadienyl, so this cyclopentadienyl will donate the electrons to the molybdenum center. Okay, and this molybdenum bond will form. Okay, so now the compound is getting dimerized. Okay, in presence of H nu, the compound is getting dimerized. Molybdenum bond is forming because you are using 2 moles of that, and this cyclopentadienyl is donating electrons. This one is also donating electrons. So basically, if I calculate the electrons, so 6 electrons from your molybdenum center, 5 electrons from this cyclopentadienyl, and 1 electron from this covalent bond. So 6 plus 5 plus 1, 12 electrons you are getting. So how many carbonyls you need? You need 3 carbonyls here, and this side also you need 3 carbonyls. So basically the metal dimerization will take place, but cyclopentadienyl will break down. Okay.
Sir, it follows associative or dissociative?
This one,
Yes, sir.
dissociative. If you have
Sir,
8,
total electron count.
total electron count will be 36. Per metal center you have to calculate, per metal center. So this one is your molybdenum center. So molybdenum has 6 electrons. The cyclopentadiene
No,
will have 5
sir,
electrons.
not this one. Starting material.
Starting material also 18 electron. Na? 6 plus 12, 18. You are using 2 equivalent of this, so that means 2 mole. So that does not mean that you have. If you take 1 molybdenum carbonyl whole 6, so you have 18 electrons. Na?
One bridging carbonyl is present, right now?
Huh?
One bridging carbonyl present between
No.
two molybdenum centers.
Here.
Yes, sir.
No, not bridging. This is an octahedral complex. Molybdenum CO whole 6. Are 2 moles you are using. 2 moles means what? Suppose I am using 1 mole. 1 moles means you have this. Molybdenum you have 6 carbonyl like this.
Okay, sir. Okay.
Octahedral complex. Now you are using 2 mole of this. That's it.
Okay, sir.
Okay.
Clear.
Hmm. So next you have this, okay. So in presence of H nu, what will happen? So first of all, tell me how many electron system it is, then we will do. How many electron system it is?
Yeah. 18 electrons, sir.
18 electrons. So what will happen in presence of H nu? Hmm? 18 electron means what? Hmm? Associative or dissociative? Dissociative mechanism will take place, na? Dissociative mechanism. So that means what? One of the carbonyl will leave from here. Okay. One of the carbonyl will leave from here. So if one of the carbonyl leaves from here, what you are getting? MnCO whole 4. Right. So now you are getting 16 electron. Right. This is
Yes,
what?
sir.
This is actually your known as your fluxional ligand. Why it is called fluxional ligand? Now we will see why it is called fluxional ligand. So here only one carbon is attaching with your manganese center or metal center, so that means I can say here you have eta 1, right? If
Yes,
one
sir.
carbonyl leaves from here, so you are getting basically 16 electron by this dissociative mechanism. Okay, next step will be what? Next step will be like this: 1 2. So just carve it. Okay, same thing we are drawing. So already this carbon center is attaching with your manganese center. You have 4 carbonyls, 16 electron, right? If I draw like this one also has 16 electron, right?
Yes, sir.
Now suppose this pi bond also donates electrons to this manganese center, so what will happen? 18 electron,
18 electron.
right? So the same thing I can draw like that also. Okay, so you can show like this. Both are same. Okay, if in exam they are showing like this, so that means this one and this one is same. So here it exists as your what? Eta 3. Why? Because this carbon center is donating and here pi electrons are donating, right? So that means all the 3 carbons are donating electrons to the metal center. So this is your eta 3. Okay, as well as it gets 18 electron to stabilize. Clear?
Yes, sir. Clear.
Okay. So this is one cyclopentadienyl ring. So in presence of H nu, what will happen? So one thing you have to notice here, this cyclopentadienyl, here I am drawing from inside the ring, right? So that means it is your eta 5. All the 5 carbon atoms are donating electrons to metal center, and here only one carbon center is attaching, so that is basically your eta 1. Eta 5 and eta 1. So first of all check how many electron system it is, then in presence of H nu, what will happen? Try to solve.
18 electron.
18 electrons. So yeah, now try to do it. What will happen?
So in second one, cyclopentadienyl, it will donate to 3 electrons.
Hmm? First step will be what? First step?
One carbonyl will leave.
One of the carbonyl will leave. So basically it is following your dissociative mechanism, right?
Yes, sir.
So first of all it will follow your dissociative
Electrons.
mechanism, right? So what I am getting, so here you
16
have,
electrons are
yeah, here
present.
you have this cyclopentadienyl ring. Okay, here I have iron center, and here 1 2 3 4 5. So yeah, so now I am getting 16 electron. Now next step, tell me.
The second one, cyclopentadienyl, it will donate 3 electrons.
Ah, so it will donate 3 electrons,
3
correct?
electrons.
So basically here you have iron, and this cyclopentadienyl I am drawing like this. So basically 1 2, so one carbon is directly attaching with the metal center, and suppose this double bond is donating electrons to the metal center, so overall it is donating 3 electrons, right? And
Yes.
here you have carbonyl, so now it is becoming 18 electron, right? Now anything is possible. Now suppose this carbonyl is also releasing. Okay, if this carbonyl release, so again it is following your dissociative mechanism. Okay,
Then it also 16 electron.
so again it will become your 16 electron, because you have this. Now 1 2 3 4 5. So this carbon center is attaching with this, and this double bond is attaching with this, and now it is becoming what? 16 electron, right? Next step will be
Yes, sir.
what? Next step will be what? So here cyclopentadienyl, so if this double bond, if it donates also, okay, suppose now both the double bond is donating electrons to iron center, so that means what? I can show like this. So then also it will again becoming 18 electron, right? So this is becoming what? This is basically this compound FeCp whole 2. So this iron metal center is sandwiched between the two cyclopentadienyl rings. So what are the fluxionality you can see? So initially here you have eta 1, okay, here you have eta 1, now here it becoming eta 3, and at last it is becoming what, eta 5,
Eta 5.
right? Now if I compare this like cyclopentadienyl, so eta 5 is the most stable. Okay, eta 5 1 is the most stable. Why it is most stable? Because eta 5 means it becomes what, it becomes your aromatic system.
Aromatic.
Okay, so this is the fluxional ligands. From eta 1 it is changing to eta 3, then it is changing to eta 5, and eta 5 is the most stable form. That's why here the this carbonyl leaves, it is getting 16 electron, and again it is becoming 18 electron. Clear?
Yes, clear.
Clear, right? Fine. Now try to solve this one. So in presence of H nu, what will happen? Try to solve it. In presence of H nu, what will happen?
The first step, one CO will leave.
Do
18
it.
electron converted into 16 electron. Then it will, the positive one converted into a positive 3.
Ah. So basically, first will be your dissociative mechanism.
Yes, sir.
So if it follows dissociative mechanism, what you will get? So here you have molybdenum. Okay. Here you have two carbonyls. 1 2. So how now I am getting 16 electron, right?
Yes, sir.
16 electron. And now if this double bond, next step will be what?
It will donate.
So basically here you have, here this ligand, it is your eta 1, here also it is eta 1. Now so 1 2 3. So basically this double bond donates electrons to the molybdenum center, and here you have two carbonyl, right? So again I am getting how many electrons? 18 electrons, and it is becoming now eta 3. That's it. Clear?
Yes, sir, clear.
Okay, fine. Okay, now next example, suppose you have this compound iodine, then you have rhenium center, 5 carbonyls you have. This compound we are reacting with silver nitrate AgNO3, okay, and we have ethylene CH2 double bond CH2 in presence of heating. Try to solve what will happen. So you have this compound, metal carbonyl compound, in presence of silver nitrate and ethylene in presence of heating, what will happen? Under heating condition, what will happen? Try to solve it. Turn off the mic, huh? So what will happen here? So silver nitrate is basically silver plus Ag plus NO3 minus, right? So iodine has lone pair. You already know iodine has lone pair. So what will happen initially? This silver nitrate which lead with the iodine center, or you can say that iodine will donate the lone pair with silver plus to silver plus. Okay, so once it donates the electrons to silver plus, so that means the silver center will be neutralized. So I can draw it like this, that Ag, iodine, then you have rhenium, CO whole 5. Now see, iodine is donating electrons, iodine is donating lone pairs, so it will be positively charged. Silver plus is taking electrons, so it will be neutralized, no charge. So now iodine is getting positively charged. So I want to, like, iodine wants to neutralize, so what will happen? This bond will break, electrons will come to the iodine. So like iodine will be neutralized and you will get this salt, silver iodide. This salt you are getting, and rhenium will get which charge? Like on this metal center, rhenium center, which charge will left?
Positive charge.
Positive charge will left. So that is the scenario, right? So now you can see how many electron system it is. So rhenium means you have 7
Electron.
electrons. From 5 carbonyls you will get 10 electrons, and if you have
Minus
positive
1.
charge, so you will get minus 1. So I have only 16 electrons here, right? Here I have 16 electron. Now if you see here, they have given you this ethylene compound, okay, with this rhenium. So what will happen in presence of this ethylene?
It will
CH2.
donate 2 electrons.
So this ethylene will donate 2 electrons to the rhenium positive center. So basically I can draw it like this, that CO whole 5, then you have rhenium, you have a positive charge here, and here you have this ethylene system, CH2 double bond CH2. It is donating 2 electrons to the rhenium center. So you will get here 18 electrons, and this is the thing. Now basically they can show this thing like this positive charge they cannot show on rhenium, okay, they can show here overall charge positive. Okay, so if they are showing the positive charge on rhenium center or here overall charge, both thing is same. Okay, both the things are same. Okay, so that means this overall positive charge is basically the charge on the metal center. Okay, clear?
So that time total valence electron 17.
Where
The positive charge is present.
positive charge is present overall, so that time also you will get 18 na?
Minus 1.
Huh.
Uh,
7 electrons from your rhenium, from 7 electrons from your rhenium, you have 5 carbonyls, so that means you are getting 5 into 10. From this double bond, from this ethylene double bond, you will get 2 electrons, and for that positive charge you will get
19.
minus
Got
1.
it, sir.
Add them, you will get 18 na?
Yes, sir.
Clear?
Yes, sir, clear.
Now do this. So first of all, calculate how many electrons you have, then in presence of each nu what can happen.
18 electrons, sir.
uh,
One CO will leave. Then it will form
so
16
18,
electrons.
yeah.
Then form 18 electrons, capacity 3.
So basically 18 electrons, so it will follow dissociative mechanism. One of the carbonyl will leave, and if one of the carbonyl leaves, so what I am getting, so here you have cyclopentadienyl, okay, here you have iron 1 2, this thing you have, here you have carbonyl CO. So how many electrons I am getting now? 16 electron. Next step will be what? So you have this cyclopentadienyl. Okay, next step you have iron, you have CO, and this thing 1 2 3, right? So this thing will happen. So again you are getting 8 electron. Here it is acting as your eta 1, this ligand, but here it is acting now as what? Eta 3. That's it. Clear? Done?
Yes, sir. Clear, done.
Next you have this 1 2 3 4 5. So here you have iron, okay, CO 1 2 3. So this is the thing we have. So now in presence of H nu, what can happen? Do it.
It is 16 electrons. So the pi bond, it will donate 2 electrons to fluorine metal iron center.
16 electron. So 16 electron, then what can happen?
The pi bond, it will donate 2 electrons to the metal center. Then it will form 18 electrons.
Okay, fine. So basically, so this is the cyclopentadienyl thing you have. Here you have iron. Now 1 3. So if you have 16 electrons, so that means here it will follow associative mechanism, not dissociative. Okay.
Yes, sir.
So it will follow your associative mechanism. So one center now, yeah. So this double bond will donate the electrons, and you have carbonyl, so you are getting 18 electron. Okay.
Yes, sir.
18 electron you are getting. Now what will happen? Now this carbonyl will leave from here, because initially you have 16 electron, so it will end in your 16 electron. Yeah, so carbonyl will leave from here, and ultimately you will get this. So iron, and this thing I am drawing like this. Okay, so again you are getting back 16 electron. Okay.
Yes, sir.
Okay, fine. Now write down one thing, that
coordination number of metals and
coordination number, here it is eta 3 now. Here it is eta 1. Coordination number of metal center, so here it is 1 2 3, but now it is becoming 1 2 3 4 5. TBP structure you will get. Okay, and ultimately you are getting 1 2 3 4. Here the coordination number will be 4. Just see how many carbon centers are attaching with the metal center. Okay. Here basically you will get like all the 5 carbons are donating. So yeah, that is the scenario. Yeah, 1 2 3, it will be 1 2 3 4. Here it will be 3 and 4. Yeah, fine. Okay, now next write down one para, that 18 electron species. Write down with me. 18 electron species generally undergo substitution reaction. Generally undergo substitution reaction via dissociative mechanism. That you already know, that if you have 18 electron compounds, it will follow dissociative mechanism. Okay, but it is not the case, like all the time it will not follow this. So write down that however However, if a polyhaptoligand polyhapto polyhaptoligand is present on the metal, polyhaptoligand is present on the metal, present on the metal, and it can adopt it can adopt a lower hefticity. It can adopt a lower hefticity. The reaction can proceed the reaction can proceed through reaction can proceed through associative mechanism as well. Okay, so 18 electron species generally undergo substitution reaction via dissociative mechanism, that we already know. But if you have some polyhaptoligand, okay, and the metal can adopt a lower hapticity, that time the reaction can also follow associative mechanism also. Okay,
Okay.
clear. So suppose you have this kind of ligand, uh, so this is an indole type of thing. Okay, so 1 2, and suppose here you have this. Okay, so if you see, if I talk about only this 5-membered ring, so now it is actually your eta 5. Why eta 5? Because this is one carbon center, this carbon you have one double bond, this carbon you have one double bond. So basically they will all, like, all the pi electrons will donate and you will get eta 5, right? Now the same compound I can also write down like this. The same compound I can also write down like this. And if I write down like this, so that times it will be your eta 3, not eta 5. Why eta 3? Because this negative charge will donate, and this you have only one double bond, so that will donate, not this, because now this double bond is part of your benzene ring, part of this 6-membered ring, not your 5-membered ring. Now tell me, which one is more stable? Which one is more stable, this structure or this structure? Same compound,
Eta
but we are
5.
writing
Eta
two.
5.
Hmm?
Eta 5.
Why eta 5?
This one is more stable.
What is the reason why it is more stable? Hmm?
Because it's aromatic.
Eta 5 is aromatic. Here also you have aromatic. Benzene ring is also aromatic. In eta 5, this 5-membered ring is aromatic, that is correct. But here you have this benzene ring, that is also aromatic. Okay, fine. So write down. This one is basically less aromatic. Okay, this one is your less aromatic, and this one is actually your more aromatic. So in GOC, when we have done GOC in organic chemistry, that time I, we have no we know one thing, that is actually your annihilation effect. So what is annihilation effect? So you can see this benzene ring is aromatic, right? And suppose in the adjacent position you have a negative charge in the cyclic ring. So basically if you have a cyclic ring and you have benzene this aromatic ring is there, so that time what will happen, that time the aromaticity is actually coming to this ring also. Okay, aromaticity will spread out. Suppose another compound, it is like this, you have two 5-membered rings in the two sides, and in the middle you have benzene ring, and you have two 5-membered rings. So that time the aromaticity will spread out in the both direction. Okay, both the direction the aromaticity will spread out. So basically this is your annihilation effect. So this is like your charge. So basically the electrons are flowing, electrons are getting conjugation, and they are flowing to the side rings also, and the compound is becoming more aromatic. Okay, so that is basically your annihilation effect. But here it is not possible, because here the benzene ring is not aromatic. This ring is aromatic, but this ring is not aromatic. Here what is the scenario? Here benzene ring is aromatic, this ring is not aromatic. But what is happening? The aromaticity is actually flowing to the side rings, to the adjacent rings. Okay, if you are attaching one 5-membered ring, so that time also the aromaticity will flow to that ring also. Okay, so that is your annihilation effect. And if this kind of thing is happening, so that means this is getting more aromatic, and this one will be your more stable. Okay, this configuration is becoming more stable. Clear? So this is basically your polyhaptoligand. Okay, this is basically your uh, like it can adopt a lower hapticity as well as polyhaptoligand. Okay, so one example we are doing now.
Sir,
Huh.
a 6-member ring aromaticity will spread out. Of a 5-member ring will not spread out the aromaticity.
No, because this one is not aromatic, na. This one is not aromatic. Now, if you see here the conjugation, here it will be like this. So it is locked within this 5-membered ring only. Okay, but if you see here, that time this double bond is in conjugation with this, right? So
Oh,
basically,
sister.
uh, basically the aromaticity is spread to the side ring also.
Okay, sir.
Okay, clear? Here the aromaticity is locked within this 5-membered ring only. Okay, but here it is actually spreading to the adjacent rings also. Okay,
Yes, sir. Yeah.
fine. Now suppose you have this thing. Okay, just a minute. Huh? Suppose I have 1, 2, 3, 4, 5, 6. Okay, and this side you have 1, 2, 3, 4, 5. Okay, so here I have 1, 2, and this side you have this. Okay, here you have rhodium. Okay, and 2 carbonyls. Okay, so basically here you can see this is your eta 5. So how many electron system it is? First of all, calculate that. How many electron system it is?
18 electron.
18 electrons. So what will happen?
On in presence of 8 some
Mm-hmm.
dissociative mechanism it will
Dissociative
follow.
mechanism here it will not take place. That's what actually I am trying to say. Here it will not do dissociative mechanism. Okay, so if you see, this is your polyhaptoligand. Okay, this is your polyhaptoligand. So you can see here it is present in eta 5. Right, if you have polyhaptoligand, and if it has like the possibility it can adopt a lower hapticity value, so it will does that. So here basically it is present in eta 5, but eta 5 is not that much stable. Eta 3 is more stable. So it will now change itself to eta 3 configuration. So what will happen? So basically here I will get 1 2 3, and this side you have a 5-membered ring. Okay, so now you will get like this, or you can show like this a double bond here, and that is also attaching to your rhodium center. So I am showing like this. So here you have rhodium, okay, and these two carbonyls you have, okay. So initially you have 18 electron here, okay. Now
16
here it is,
electrons.
yeah, here actually what is happening here, it is actually
Eta 3.
rearranges to eta 3 configuration, and now it will occupy how many electrons? 16
16
electron,
electrons.
okay, 16 electron. Now suppose we are introducing one ligand PME3, okay, trimethyl phosphine. So that time what will happen? So that time what will happen? So here you have rhodium, you have two carbonyls here, okay, and here you have PME3, right? So basically associative mechanism is happening here. So see, if you have 18 electron, that time also associative mechanism is possible, but not by dissociative mechanism. What it is doing, it is just changing its hapticity value. So you are getting lower hapticity value now, and then associative mechanism is possible, okay.
Yes.
But one thing will happen, so if you have more ligands, so that means the repulsion will generate, okay. So that time, now next step, one of the CO will remove from here. So here you are getting 18 electron, now one of the CO will remove from here, and then what you are getting, then you are getting
16 electrons.
uh, not 18 electrons, yeah, 16 electron.
16 electrons.
So that time you will get rhodium is here, okay, pph3 is here, carbon is
PME3.
here, yeah, 16 electron is here. Now 16 electron you are getting, so how can you make it 18 electron? So here it is your eta 3. If it again changes to eta 5, because initially it was present in eta 5, so again make it eta 5. So you just make like this, then this 5-membered ring, make it aromatic, okay. So that means that time what you will get, you will get 18 electron. Here it is what, it is your eta 5, okay.
Yes, sir.
That is the scenario. So if you have this kind of polyhapto ligand and lower hapticity is possible, that time it will do associative mechanism, okay. Clear? Done? Any doubt? Tell me. Any doubt in this example?
No, sir.
No, right? Okay, fine. Now next, write down rate of reaction, okay. So I am giving some examples here. So here you have 1 2 3 4 5. Here I have rhodium, CO, this thing you have. Now 1 2 3 4 5 6. So 1 2, here I have 5 rings, 1 2 3 4 5, okay. So here also I have rhodium, CO, 1 2 3 4 5 6. So this ring you have, then you have a 5-membered ring here, then 1 2 3 4 5 6. So here you have again this thing, it is attaching to your rhodium center, you have 2 carbonyl. Okay, and next you have this. Okay, so these are the 4 compounds you have. This is your compound A, this is your B, this one is your C, and this one is your D. Now tell me the rate of reaction.
So DCBA.
DCBA, why?
Because D1 is less bulky.
D1 is your less bulky. Okay, not here, actually not bulky. First of all, you check all the things like how many electron system they are. Okay,
So all are 18 electrons.
ah 18 electrons. So what can happen, that is the thing, no? So if you see your compound A and D, compound A and D, so basically uh, here this 5-membered ring is aromatic, here this is also your aromatic, but here annihilation effect is present, right? This ring is actually your aromatic. So this is happening, okay, annihilation effect is present, okay. Here double annihilation is effect is present, okay, double annihilation effect is present, okay. So basically what is happening, if you see the electron density, the electron density is highest in compound A. Why? Because you have 5 methyl groups attached to this cyclopentadienyl ligand, right? So the electron density is very highest here. Next will be this one, and next will be your B, and next will be C. Why C? Because here the electron density, the aromatic is actually spreading to the adjacent to aromatic rings, okay, adjacent to these rings, okay. And if your electron density is high, so what will happen, if electron density is high here, so that will donate to the metal center, and once it coming to the metal center, metal will back donate the electrons to the pi star orbital of your CO, okay. So that means if you have more electron density, more back bonding will happen, okay. And if more back bonding is happening, so that means the rhodium carbon bond, this bond is now becoming very strong, okay. This rhodium carbon bond is now becoming very strong, it cannot dissociate. So that means if you have 18 electron already, so the first step is your dissociative mechanism, right? One of the CO has to leave, right, has to release from here, and it can only release if the rhodium carbon bond is not that much strong. So if it is getting that much strong, right, it is becoming very very strong, so that means the dissociation is getting difficult. Okay, it is becoming difficult. So you just write down that if electron density is high, so you just write down that more back bonding, okay, due to cyclopentadienyl CP star ligand, okay, CP star ligand. And if back bonding is happening, so that means what is happening, the rhodium carbon bond becoming more strong, more strong. So what is happening, dissociation of CO becoming what, dissociation of CO becoming difficult. Okay, so if your electron density is high, the metal will back donate the electrons, the back bonding possibility is also increasing. So here in compound, if I show you the electron density order, so A will have highest electron density, next will be your D, next will be your B, and the last and the least one will be your C. So if electron density is that follows this order, so that means the back bonding is also following this order. So that means the reaction rate will be what, reaction rate will follow the opposite order. Okay, because more back bonding, more strong bond, the CO release will become much more difficult. Clear?
It's not clear.
Clear, right? Fine. Now suppose you have this CO whole 3 cobalt, and this is your nitrosyl ligand. Okay, so here I am giving you H nu in presence of PPH3 ligand. Tell me what will happen, try to do it. So this nitrosyl, how many electron it donates? This nitrosyl ligand. Hmm? Linear nitrosyl, bent nitrosyl, you remember linear nitrosyl, bent nitrosyl. So this nitrosyl is basically your linear nitrosyl. If you have
3 electrons.
3 electrons, it will donate 3 electron cobalt. From cobalt center you will get 9 electron, and from 3 carbonyl center you will get 6 electron, right? So overall you
Yes,
have
sir.
already 18 electron. Now what can happen? Now don't do initially dissociative mechanism. It will not follow dissociative mechanism. If you remove one of the carbonyl, it will be wrong. Why? Because you have polyhaptoligand. Polyhaptoligand means what? What is the definition of polyhaptoligand? So that means you have more than one hapticity. If you have only eta 1, so that is your fine monohapto. But if it is able to find eta 3, eta 5, okay, or they can like do like lower hapticity value, okay, they can do. But here actually it is your monohaptoligand, but another thing is possible here. What can happen? So this linear nitrosyl, suppose you have already a linear nitrosyl, okay, fine. Now this nitrosyl, if it adopts a bent structure, okay, suppose it adopts the bent structure like this. So this is your bent nitrosyl now. So in presence of H nu, if it adopts a bent nitrosyl structure, so that means what? Now it will get 16 electron. Okay, and once it gets 16 electron, pph3 will donate the electrons. Okay, so pph3 will donate the electrons, sorry, to the metal center, not to the nitrosyl. pph3 will donate the metal electrons to the metal center. So what I have, so here I have CO whole 3, then you have cobalt. Okay, nitrosyl ligand is attaching here. Okay, and pph3 is also attaching here. So what you are getting, again you are getting 18 electron. Clear?
Yes, sir.
Now if you are getting 18 electron, after that you can do dissociative mechanism. Here you can do dissociative mechanism. Okay, because now your this nitrosyl cannot adopt any other geometry. Okay, from linear it comes to bent, that is enough, fair enough. Now addition is like introduction of the new ligand is also done. So now one thing is left, that is your removal of the ligand. Okay, or dissociative mechanism. So now what you will get, you will get CO whole 2. Okay, then you have cobalt, you have here bent nitrous, sorry, you just show like this, you have this bent nitrosyl. So if one of the CO leaves, so again it is becoming 16 electron, and what will be the last step, can you tell me? The last step will be what? So basically the bend is now coming back to its your linear
Linear.
form. Okay, if it come back to linear form, so that means what, it is now donating 3 electrons, so it is again becoming what, 18 electron
18.
species. Okay, so basically that is the scenario. Clear? This example is clear. So how
Yes,
without
sir.
dissociative mechanism reaction can happen, that is possible if and only if you have polyhapto ligand. Okay, as well as the metal center can adopt lower hapticity value. Okay, that time through associative mechanism also you can do. So this is basically what, pph3 is donating electrons, this is basically your associative mechanism. Okay, so these kind of reactions, they have initially they have 18 electrons, but still they are following associative mechanism, not dissociative mechanism. Okay, clear?
Yes, sir. Clear.
Fine. Now see, next suppose you have a thing like this, suppose you have ligand, so I am writing ln. Okay, because you have n number of, it's better to write down like this. Suppose you have ln, these are the ligands you have metal, and this is your metal iodide bond, metal halogen bond you have. Now if I treat this compound with this lithium aluminum hydride, so basically what you have, you have H minus, so H minus will attack on the metal center, iodide will leave from here. If you treat this compound with this metal lithium aluminum hydride, so what I will get, I will get this LNMH. Okay, so similarly I can show you some reactions. So basically suppose you have this cyclopentadienyl ring, then here you have iron, here you have two carbonyl, iodine is also present there. Okay, fine. Now first of all I am treating this compound with lithium aluminum hydride, so can you tell me what will happen? So how many electrons it is, how many electron compound? How many electron
18
system it
electrons,
is?
sir.
18 electron, right?
Yes, sir.
So basically what will happen? What is the reaction? If you are treating this with lithium aluminum hydride, so H minus will attack the metal center, iodine will leave from here. Okay, H minus will attack the metal center, iodine will leave from here. And what I am getting basically, so here you have Fe. Okay, so here you have carbonyl, and hydrogen is there. Clear?
Yes, sir.
Suppose I am treating this compound, same compound, I am reacting with methyl magnesium bromide, Grignard reagent. So what will happen?
CH3 minus it will attack metal
Uh,
center.
so that
Iodine
time
will leave.
CH3 minus, yeah, correct. So that time CH3 minus is the nucleophile, so it will attack on the metal center, iodine will leave. So what I am getting? So you
It
have
is
this,
also
yeah, you
getting
have this
electrons.
cyclopentadienyl ring. Here you have iron center. Okay. Uh, you have two carbonyls and CH3 is attaching here. Okay, clear, done.
That's all clear.
Fine. Another thing. So you have this compound, same compound. Here I am treating with silver nitrate, initially with silver nitrate number 1, and number 2 they have introduced acetylene. Okay, acetylene. So can you tell me what will happen? Do it.
Silver iodide will leave. Then
So first of all,
in metal center it will attack the triple bonds.
hmm, first of all
Carbon
what will
center.
happen? First of all, iodine will
Iodine will attract the
coordinate with the silver plus,
silver.
right? Iodine is donating the electrons to silver plus. So what is happening? So you have this cyclopentadienyl ring. Okay, here you have Fe, iron center. Uh, two carbonyls are also present.
Iodine carries positive charge.
Iodine is getting positive charge and silver is getting
Okay.
neutralized, right?
Neutral.
Next will be what? Iodine wants to
Neutral.
neutralize, so this bond will break. Once the bond breaks, so AgI, see, electrons are coming to here, so AgI is getting neutralized, and iron is getting which charge? Iron is now getting
Positive
positive
charge.
charge. Positive charge, correct. So you have the CP ligand here, positive charge is here. Okay, once it gets the positive charge, so how many electrons you have now? You can see 16 electron you have now. Okay, and in the second step what they have given? They have given acetylene. So if you have acetylene, so what will happen? Acetylene will donate the electrons by one of the pi bond. Okay, acetylene is not donating both the pi bonds. One of the pi bond is donating two electrons to the metal center, and what you will get? So I can draw it like this. This thing, then you have iron, then you have two carbonyl. Okay, and this side you have what? Acetylene. Okay, this thing, and you can show the whole positive charge here outside of the bracket. Again you are getting 18 electron back. Clear?
Yes, sir, clear.
Fine. So few more reactions we have that we will do tomorrow. Okay, because that is a separate, that is not a separate topic, but yeah, new concept will be there, so it's better to do it tomorrow. And then we will go to metal carbonylates. It will take some time because this organometallic chemistry is a very vast chapter. You will get questions from here, but it's a very vast chapter, so it will take some time. Okay, I think one more class it will take only for the reactions. Okay, and after the reactions is over, that time we can like move to the mechanism part. Okay, like oxidative mechanism, reductive elimination. So yeah, that is the scenario. So hardly it will take, I think, yeah, 6 to 7 classes. It will take more. Okay, fine. Any doubt? You can tell me, huh?
Yes, sir.
Okay,
Clear, sir.
clear, right? Okay,
Yes, sir.
fine. And physical chemistry you're following? Physical chemistry you're not attending physical chemistry at all?
Yes, sir. Group theory, it is difficult to me.
Difficult? Okay. Tell me, just uh, follow the lectures and tell me where you have doubt. Okay.
Okay, sir.
Okay, fine. Okay, and practice organic chemistry also. Okay.
Okay, sir.
Okay,
Thank
bye.
you, sir.
Bye. Thank you.